Yes, thank you. Yeah. Professor saw it a little bit exaggerated on me, you know. Anyway, it's my pleasure to talk here. It's a beautiful and sunny sky, and also it's a nice campus. And I visited several times Kyungpoong University. So whenever I visit Kyungpoong University, I'm always, you know, pleased, and also feel free, you know. So thanks so much again for invitation. Okay, as you see, do you hear me? The backside? Do I have to use mic? Do you hear me on backside? Okay. Okay, as you see, the title of my talk is Exotic Smooth Structures on Four-Manifold, and Professor thought, you know, that to introduce me, I'm a topologist, not differential geometers, but you know, the research area is close related to the differential geometry, you know. Okay, let me start with some basic the notion or object in mathematics. As you see, the manifold is one of the most important objects in geometry and topology, and you learn the notion of manifold in undergraduate, you know, the course. So this manifold is, roughly speaking, is locally Euclidean space, right? And of course, in Hausdorff separately this is some extra conditions. And without any conditions, extra conditions, you know, you'll see that then whenever we have at any point it's a locally Euclidean space, then we call this a topological manifold. But you know, if this manifold is just a topological manifold, in some sense, it's nothing interested. When the mathematicians study this manifold, and we usually input some geometric structures. For examples, the most typical one is the diffeomorphic conditions. What I mean, on overlapped, if the composition of this transmap is smooth, then we call this is a differentiable manifold or a smooth manifold. So also, you know, you'll see if the overlapped, if this composition of this transmap is holomorphic, then we call this a complex manifold. In the real sense, then the complex manifold always the even dimensional manifold. Besides these smooth or differentiable structures, as well as the holomorphic structures, there are many other geometric structures. And for examples, the simplex structures, almost complex or Kähler, and sometimes algebraics. Okay, let me just briefly introduce for these various geometric structures. What is the symplectic structures? The symplectic manifold is the even dimensional manifold which admits non-degenerate class 2 forms. We call that the symplectic forms. Okay? And it turned out the symplectic manifold is in what I mean, the locally symplectic manifold is always symplectomorphic. What I mean, there is no distinctions on the locally. That means the symplectic structure is the global structures. It is determined by the global feature of this manifold. And the almost complex structures, as you see, you know, whenever the manifold is a complex manifold, then that complex manifold inherits the standard complex structures. But sometimes some smooth manifold admits complex structures on its tangent bundle, which does not come from its manifold. Okay? And so the almost complex structures, by definition, is the smooth vector field of complex structures. What I mean, this complex structure J means, you know, the J composition J is minus identity. It's like you know, the minus I, the imaginary numbers. And so whenever we have this this smooth field of complex structures, and we call these almost complex structures. And it seems, although it seems is very, the local structures, and it turned out these almost complex structures is topological structures. This is determined by some topological conditions. Okay. Whenever, what I mean, if this manifold satisfies some topological conditions, then it admits the almost complex structures. Okay. Of course, the complex manifold, as I told you before in the previous page, is a set of complex atlas together with the bioholomorphic transition maps. Whenever we have the complex atlas with the bioholomorphic transition map, then we call the complex manifold. And there are more delicate geometric structures. For example, the Kähler manifold or Kähler structure. The Kähler structure is the Kähler manifold is a symplectic manifold. They keep to its integrable and comparable almost complex structures. Integrable means, you'll see for this smooth manifold, you'll see the Nienhaus tensor, and whenever you have the vanishing Nienhaus tensor, then we call the integrable. And also there is a Riemannian metric, and also there is almost complex structures. They are all comparable, then we call the comparable almost complex structures. Equivalently, you can say this complex manifold is a complex, Equivalently, this Kähler manifold is a complex manifold. You keep to is the Kähler metric. The Kähler metric means, whenever you have the complex manifold, then it has automatically the Hermitian metric. And this associated unknown form of its Hermitian metric is closed, then we call that's the Kähler manifold. And we say that associated unknown form is the Kähler metric. Okay? In fact, Kähler form, whenever that is closed, then we call that Hermitian metric is the Kähler metric. Okay? And among these various geometric structures, I have one more. It's that's the algebraic variety. The algebraic variety means in CPN is the zero locus of homogeneous polynomials. And sometimes this algebraic variety contains a singular point, and sometimes this algebraic variety is a smooth manifold. And among these various geometric structures, we can see the relations like this. What I mean, this algebraic structure or algebraic variety is the most fine structures. In case this is a smooth case, what I mean, there's no singular point. Then there is automatically is a Kähler manifold, and if Kähler manifold is automatically complex and symplectic. And it turned out there's no relation between the symplectic manifold and complex manifold. And for example, in an S1 cross S3 is a Hopf manifold, is a complex manifold, but it does not admit symplectic manifold. So there is some overlap, but most case symplectic manifold, the complex manifold is symplectic manifold, with a few exceptions, like a Hopf manifold. And anyway, it is symplectic or complex manifold is almost complex structures, almost complex manifold, and also these are contained in smooth manifold. In some sense, the smooth manifold is the most large class among the category of the manifold, and this is the most defined families. And the algebraic geometers and complex geometers are studying these categories, and nowadays symplectic geometers and also differential geometers study this symplectic manifold, and like me and the four manifold topologists and the geometers studying this smooth manifold category. But in order to study smooth manifold, sometimes we need to study symplectic manifold. And even we need some Kähler or algebraic structures, because the most typical examples of smooth four-manifold comes from the complex surface. And also, this symplectic manifold, sometimes this symplectic manifold contains some properties. What I mean, this shares with some common properties with smooth manifold, and sometimes the properties of the symplectic manifold reflects on the property of this Kähler manifold. So this symplectic manifold is the bridges between the smooth category and the complex categories. And also, you see this, the Kähler manifold or algebraic variety is so rigid. What I mean, if you want to change locally this algebraic variety, then it turned out, in most cases, it is not algebraic variety anymore. So it's very rigid. And in smooth category, it's very flexible. What I mean, in order to construct some smooth manifold, usually we can cut and paste techniques. So locally we can construct smooth manifold and then patch or paste to construct another new smooth manifold. And for this symplectic manifold, sometimes it works, sometimes it doesn't work. So in more or less, the symplectic manifold is enough to flexible and enough to be rigid. So the study of the symplectic manifold is play an important role in studying both smooth category and complex categories. That is one of the reasons why the symplectic manifold is important in geometry and topology. Okay. It's my favorite questions. So why topology geometers are interested in smooth four-manifold rather than other dimensional manifold? Of course, the answers depends on each person, right? And I'd like to answer with this question. They say, in 1982, Simon Donaldson introduced gauge theories. Before he introduced, there's nothing known for smooth four-manifold. And it turned out this dimension 4 is strikingly different from the other dimensions. And for examples, if the dimension of the manifold is less than or equal to 3, then topological manifold automatically admit smooth manifold. What I mean, whenever you have topological manifold, that means you can choose the maximal atlas to be this topological manifold. Among these maximal atlas, you can find some sub-atlas whose transition map is differentiable. So in that sense, we call any topological manifold of dimension is less than or equal to 3, then automatically it admits smooth manifold. And if dimension is greater than or equal to 5, then given topological manifold, then there are at most finitely many smooth structures. Sometimes empty, but the point is at most finitely many smooth structures. And how about dimension 4? And before, until 1985, there's nothing known about this one. And then after the Donaldson introduced the Donaldson invariant, and in mid-1990s, Seiberitten came out, then we know the most smooth four-manifold admits infinitely many smooth structures. Okay? And we call sometimes it's a smooth manifold said to have exotic smooth structures if it admits more than one smooth structures. So the terminology exotic smooth structures comes from this, the more than smooth structures. So by using this terminology, exotic smooth structures and dimension 4, if dimension is less than or equal 3, there is no exotic smooth structures. If dimension is greater than or equal 5, there are at most finitely many exotic smooth structures. But in dimension 4, as you will see, there are infinitely many in most cases. Okay? Of course, still open problems, okay, whether some manifold, smooth 4 manifold admits exotic smooth structures or not. Okay, let me briefly review about this main result in 4 manifold. And as I told you, before 1982, there is nothing known, only one exception. Okay, only one, as far as I know, one theorem is known for smooth 4 manifold, that is the Rockland signature theorem. That means the signature of spin closed smooth 4 manifold is divisible by 16. It's a multiple of 16. And this is proved in 1951 or 2, and I didn't read the paper, but later, as you learn Dirac operator, then you will see the proof of this theorem by computing the index of the Dirac operator for spin smooth 4 manifold. Then you'll see that it is a multiple of 16. And this spin and the smooth manifold is the critical conditions and for these theorems. And in 1982, the Friedman, as you see, every simply connected closed topological 4 manifold is classified by its intersection form. And this intersection form, in particular, if this is simply connected, and all homological, cohomological invariant are encoded in this intersection form. And in fact, all classical invariant for topological 4 manifold are encoded in the intersection form. And that Friedman proved there is one-to-one correspondence between simply connected closed topological 4 manifold and its intersection form, roughly what I mean. In non-spin case, there's 2-to-1. Spin case, that's a 1-to-1 correspondence. And Donaldson also proved there is some intersection form, there is no corresponding smooth 4 manifold. For examples, no simply connected spin closed smooth 4 manifold with definite intersection form. The definite intersection form means for some second homology class, its self-intersection number is positive. For some, the definite intersection form means for any second homology class, its intersection form is always positive or always negative. Then we call this a definite. And the Donaldson theorem says, there is no such simply connected spin closed smooth 4 manifold. Okay? And these two works, Friedman and Donaldson got field medals in 1986 because of these two works. As even though most mathematicians not working in geometry and topology knew this result because they are so famous result. But in study of 4 manifold, of course, this really is a great theorems, but in the theory, in the development of the theory of the 4 manifold, this is more important, I think. What I mean, in 1982, Donaldson introduced the Donaldson polynomial to prove this Dolgachev surface which is homeomorphic to this rational elliptic surface. This is diffeomorphic to CP2 connected some 9 times CP2 bar. What I mean is 9 times blowing off from the CP2. We call this is rational elliptic surface. It's known before this Dolgotchev surface is homeomorphic to this. And the people expect this Dolgotchev surface is not diffeomorphic to this standard rational elliptic surface. But there is no way to prove whether it's really diffeomorphic or not. And in 1985, Donaldson introduced the Donaldson polynomial, and by using it, he proved this one is not diffeomorphic to E1, but homeomorphic to this. And as far as I know, this is the first examples which are homeomorphic to each other, but not diffeomorphic to each other. That means this E1 admits exotic smooth structures. But we know at least 2 distinct smooth structures by pulling back from this. Right? Because these are homeomorphic or smooth manifold, we can pull back the smooth structures from this one to this. So this one admits at least 2 different smooth structures. So since these examples, there are many the fruitful and the big progress in the study of exotic smooth structures and four manifold. And that's the topic of my talk today. And what's the goal in study of this smooth four manifold? What I mean in study of the exotic smooth structures and sometimes the existence of four manifold, and we call roughly that the geography problems. So the goal is to solve the geography problems of simply connected four manifold in smooth, sometimes symplectic category, sometimes the complex category. And more specifically, these geography problems consist of the existence problem and uniqueness problems. The existence problem means which lattice point in this chi and the Sion square plane or coordinate are realized simply connected, irreducible, smooth, or complex, or symplectic four manifold. Okay? And this existence problem and is originally studied by the algebraic geometers in complex categories. They use this coordinate chi and Sion square. Sion square is these Chern numbers. Chi in complex category, this chi means holomorphic Euler characteristics. Then we extend this holomorphic Euler characteristic to the smooth category, and then we just define this one as signature plus Euler characteristic divided by 4. And the uniqueness problem means if there exists simply connected smooth or symplectic or complex manifold corresponding to lattice point, then how many distinct or how many exotic smooth or exotic symplectic or exotic complex structures on it exist? Okay? In other words, how many distinct smooth structures or exotic smooth symplectic structures on exist? So we call this existence problem and the uniqueness problems the geography problems. And the equivalently, you can say the classification of the simply connected four manifold is the geography problems of the simply four manifold. And the people might ask, why simply connected? Because simply connected is the simplest one. Up to dimension 3, simply connected condition is a critical condition in the classification problems. For example, the three-dimensional case, if simply connected three-dimensional manifold closed, that is the Poincare conjecture. S is only the S3, right? But in dimension 4, any finitely generated presented group is realized as the fundamental group of smooth, even symplectic four manifold. So fundamental group is not good invariant in the classification of four manifold. And among the fundamental groups, the simplest one is a trivial one, is a simply connected one. And even though we input these simply connected conditions, there are so many smooth, even symplectic, even complex surfaces. So we want to try to classify simply connected one first. Okay? Topological categories, that's classified by Friedman's result. And the next steps, we want to classify simply connected smooth manifold and sometimes and then symplectic and the complex the manifold. And the irony is, the simply connected or the complex manifold, complex surfaces has been studied a long time by algebraic geometers, and it has many results. And then after 1980s and the geography of symplectic and also smooth manifold and has some the proper result. So for examples, let me review about the geography of complex surface first, because this one has the long history. Roughly speaking, we can classify all complex surfaces. Complex surface means real dimension 4, but complex dimension 2. Okay? Roughly speaking, all complex surfaces into the following three categories. The rational ruled surface. In this case, we want the minimal case, elliptic, and others. And of course, what is rational? Rational is just CP2 or blowing up of CP2. And the ruled surface is a CP1 fibration over CP1. That's a rational ruled surface. Or irrational ruled surface is a CP1 fibration over Riemann surface. And so topologically, the rational ruled surface is a CP2 or it's blowing up, or CP1 fibration over CP1. Okay? And this one corresponds to codiral dimension is negative infinite. And also it should satisfy, the holomorphic Euler characteristic should be 1, and the C1 square should be less than or equal to 9. This rational ruled surface lies on this line. On this line. Let me first read here. Okay? Of course, okay, this rational ruled surface lies below, can be below this horizontal axis. And this elliptic surface means it admits elliptic vibration, and this corresponds to codiral dimension is 0 and 1, and that should satisfy C1 square 0. That is the reason why we call this horizontal line is the elliptic line, and all elliptic surfaces lies minimal case. What I mean lies on this horizontal line. And except this rational ruled surface is an elliptic surface that we call the general type. Yeah? And it turned out, of course, the more mathematically, this general type is corresponding to is a codiral dimension 2, and that should satisfy holomorphic Euler characteristic positive, C1 square positive, and most importantly, C1 square lies between 2 chi minus 6 and 9 chi. We call this C1 square equal 2 chi minus 6 is a ladder line, and this C1 square equals 9 chi called Bogomolov-Miyaoka-Yau line. And all complex surface of general type lies between these two lines, and in some sense we call this is the lower bound, this is the upper bound. And whenever you try to find, whenever you study classification problem, it's always important to find lower bound and upper bound. Yeah. So you can classify these complex surfaces in this way. And for the complex structures and at each, the most lattice point lying between this line and this one are realized by complex surfaces. And also there are finitely many complex structures which are deformation equivalent. So they are well studied. And how about symplectic and smooth structures? And by using Seiberg-Witten theory and Knoop-Witten theories, and Topps proved, in some sense, Seiberg-Witten invariant is the same as the Donaldson. Knoop-Witten invariant, and by using that fact, the Topps proved every minimal symplectic four manifold with B2 plus is greater than 1 satisfies C1 square is non-negative. That means, all minimal symplectic manifold lies above or this horizontal line. There is no minimal symplectic manifold below this x-axis, as long as B2 plus is greater than 1. Okay? That means that Topps theorem, is play a role, the lower bound, for the existence of the minimal symplectic manifold. Then the natural question is, how about the upper bound? And it's still open problems. What I mean, we don't know yet whether symplectic four manifold satisfies this Bohm-Miao-Yau inequality. And some people expect the symplectic manifold also satisfies this one, but some people not. Even, in smooth category, we don't know the lower bound and upper bound in smooth category. And one of the most famous conjecture in smooth four manifold theory is this 11-8 conjecture. That means every simply connected spin smooth four manifold satisfy the ratio of the bit to second Berry number and the signature is greater than or equal to 11/8. What I mean, the 11-8 conjecture, 11-8 line lies in here. I didn't draw this line here. So the 11-8 conjecture means all simply connected spin smooth four manifold lies above some here. Yeah. So all simply connected smooth spin four manifold lies above here. That's 11-8 conjecture. And in 1995, Mikio Furuta proved that lies 10/8 ratio here. And there's a little bit difference between this one, but this difference is really big. Yeah. And then after Mikio Furuta's result, nobody improved this one to this. But we are sure that all simply connected smooth spin four manifold satisfies this 11-8 conjecture. Okay. Yeah. But anyway, the point is, even in smooth case, we don't know about lower bound, of course, upper bound. So it's wildly open. Well, this one. That's a sort of the existence problems. And how about uniqueness problem? And by using gauge theories in the last 20 years, in the many topologists and geometers working on four manifold, and proved this one. And by summarizing in these theorems, the most known simply connected irreducible smooth four manifold P2 plus is greater than 1 and odd admit infinitely many distinct smooth structures. And in some sense, this P2 plus is greater than 1 and odd is this one is automatically come out from some gauge theories, as long as they have the non-trivial invariant. And let me explain why later about this one. And then the point is, the bottom line is this. By using gauge theories, most known smooth four manifold with P2 plus greater than 1 and odd admit infinitely many smooth structures. So dimension 4 is really different from other dimensions. No. If as I told you, at second or third pages, if dimension is greater than or equal to 5, there are at most finitely smooth structures. If less than 3, there's only one smooth structures. But in dimension 4, even in simply connected case, there are infinitely many. And what is strategies for this one? Here's the basic strategies. Given simply connected smooth four manifold with non-trivial Donaldson invariant or Seibertin invariant, suppose we have this one, and then try to find a way to produce an infinity family of smooth four manifold, which are all homeomorphic to given x, but they're mutually different Seibertin invariant or Donaldson invariant. So the basic strategy is very simple. Given smooth four manifold with non-trivial Seibertin invariant, try to find a way. That way means some surgery or some techniques to produce infinity families of smooth four manifold. But we want this one are all homeomorphic to x, but they have the different Seibertin invariant. Okay, we know Seibertin invariant, Donaldson invariant are diffeomorphic invariant. So as long as they have the different invariant, then we know they are not diffeomorphic to each other. Okay? And in the last 20 years, the people found such a way and to show or to produce this one. For examples, fibersome surgery that's introduced by Robert Gomp, and the logarithmic transformation. In fact, the logarithmic transformation is known a long time ago. And also not surgery, introduced by Fischer and Stern, and Rottinger surgery, and so on. By combining all of these techniques, they proved these theorems. What I mean, they produced the infinity family of these, all homeomorphic, but not the same Seibertin invariant. Okay? So, after this one, the natural question is, how about P2 plus equals 1? Here's the open problem. Determine which simply connected smooth four manifold with P2 plus equals 1 admits more than one smooth structures. For example, CP2 or S cross S2 or blowing up of CP2. No? What is the simplest simply connected smooth four manifold? No. Whenever you ask these questions to the students, then most students who know a little bit about manifold or a little bit about four manifold, the first example is S4. right? Standard sphere of S4. Right? And if some students knew about some algebraic geometry or it's a little bit more, then the next example is CP2 or more. Another simplest one is S2 cross S2 or CP1 cross CP1. Right? These are the simplest one, and any students who knew a little bit about the manifold or four manifold, then they have these examples in mind. And whenever, at the first time, the topologists and geometers working on four manifold want to know whether these famous and standard examples admit more than one smooth structure or not. That's the natural questions, and they really want to know about the smooth structure of this one. In particular, S4. That is the smooth version of the Poincare conjecture. And it's unsolved yet. Only unsolved problem in Poincare conjecture is this dimension 4. It's a smooth version. Huh? And since Donaldson introduced the gauge theories in 1982, and the people want to know how many smooth structures exist on such the famous examples. And after 20 years, we knew most simply connected smooth four manifold admits infinitely many. But we still don't know about these simple examples. It's a little bit irony, you know. We know the complicated examples admit, infinitely many smooth structures, but we didn't know about these simplest ones. Yeah? These are really hard problems. And for this one, except S4, this is really, except S4. This S4, we don't have any information. Okay? Even though it's really simplest one, but there's no homologies, no fundamental groups. So it's really, it's hard ones. This one has a little bit more information. For example, the second homology is non-trivial. And so we have a little bit clue for this one. And also for this one too. And what's the next simplest smooth four manifold? That is, from this one, it's a blowing up of this. So CP2 is K times CP2 bar. It's blowing up. So by blowing up K times, we got this. And also, you can blow up from this S2 cross S2. Then you will see, by blowing up once from this one, that is a differential peak 2, CP2 blowing up twice. So by blowing up from this one or this one, you will get this. So the next simplest example is this one.
So the S4 is even the structure, complex structure is unknown somewhere?
No. It's no. Even the no symplectic structures, to admit the simplex structures, we should have non-degenerate closed two form, so non-trivial second cohomologies. In closed case, what I mean, but it's no. So it's really okay. So before we got the final goal, then we want to study for this one. This one is for B2 plus equals to one case. Okay? So as I told you, B2 plus is greater than 1, then we know. And so that is the reason why it's a B2 plus 1 case is important. So there's open problems. And let me review about the history about the B2+1 case. That's topologically classified by CP2 S2 cross S2, and the blowing up of this one, that is this. Okay? And the first example is Donaldson's theorems. Donaldson's D23 is not diffeomorphic to this one. That means 9 times blowing up from this one is 9 times blowing up from CP2 admits more than one smooth structures. That's the Donaldson's seminal works. And Friedman Morgan, by using these Donaldson's polynomials, they proved there are infinitely many exactly smooth structures on 9 times blowing up. Okay? And by using the same technique, Szabo also proved if this k is greater than or equal to 9, they admit infinitely many. So everything is solved as long as k is greater than or equal to 9. So we want to lower blowing ups. So, and Diderot-Kachik proved Barlow surface. That is the only known general type complex surface with B2 plus equals to 1. And he proved Barlow surface is not diffeomorphic to 8 times blowing up. Okay? Of course, this one is homeomorphic to 8 times blowing up. That's known before. Okay? So that's the 1980s stories. And there is no progress on 1990s. And in fact, all known simply connected, even symplectic case, symplectic 4-manifold B2+1 and the positive Sion square are rational surface and Barlow surface. And so the question is whether there is simply connected symplectic 4-manifold B2+1 and positive Sion square except rational or ruled surfaces, or rational and Barlow surfaces. And in 2004, and I was able to construct simply connected symplectic 4-manifold, which is not diffeomorphic to 7 times blowing up. Of course, it's homeomorphic to this one. And the main technique is rational Brown surgeries. And by using these rational Brown surgeries, and Steve Szabo, using the same technique, he constructed simply connected 4-manifold, which is not diffeomorphic to 6 times blowing up. And Fintushel and Stone proved, in fact, this one admits infinitely many smooth structures for k equals 6, 7, and 8. He introduced some double load neighborhood, and by using that double load neighborhood, and he proved this one, infinitely many smooth structures. Basically, this one, all these examples, the technique for this one is rational Brown surgeries. And then, another one. And Szabo and myself, and also constructed 5 times blowing up admits infinitely many smooth structures by modifying these examples. Okay? And another breakthrough for new family of simply connected smooth simplex 4-manifold that came out by several groups. For example, Akhmedov and Doug Park, and Fintushel and Stone, Doug Park, and Scott Baldrige, Paul Koch in 2007 around. And they constructed infinite many smooth structures on 5 times blowing up, 3 times blowing up. And also, the main technique they use are symplectic fiber sum and Rottinger surgeries. They didn't use rational Brown surgeries. And also, the Park and the Akhmedov and show that 4 times and twice blowing up admits exotic smooth structures. And Finchel-Stern got all this one in a uniform way. What I mean, Finchel-Stern constructed symplectic four manifold, which is not diffeomorphic to this, by using some surgeries on rule homologous tori embedded in here. So, what's left? As I told you, these are the main goal for topologists and geometers working on four manifold, and we studied for this one, and we got the equivalent smooth structures for this one up to k equals 2. So what's known? What's left? S4, CP2, S2 cross S2, CP2 connects some CP2 bar. These two have the same C1 square equals 8, chi equals 1. This one has C1 square equals 9, chi equals 1. Okay? And then we solved all other problems. So these are the known these are the unknown examples. Okay? So time is almost over. Let us stop here. Okay.